What if tiny robots could adapt on the fly? This would help us develop safer and robust robots. However, there are a few limitations to solving this problem. MPC, while providing excellent control, is computationally intensive. Current approaches use pre-computed caches to enable real-time MPC on MCUs, but they require fixed hyperparameters that can't adapt to changing conditions. And using adaptive parameters traditionally require expensive recomputation of the entire cache. Recent advances in cache-embedded MPC have enabled really great results to solve this problem. The ADMM algorithm breaks down our optimization problem into 3 steps. The most computationally intensive of these is a primal update, which involves solving a linear system. Previous work involving tiny MPC shows that the primal update becomes an equality constrained QP with the same structure as a standard LQR problem, which can be solved via Riccati recursion. Tiny MPC identified that for long enough horizons, the Riccati recursion converges to the infinite horizon solution. By precomputing the steady-state cost matrix P infinity, the infinite horizon gain K infinity C1 and C2, we can dramatically speed up this process through caching. This enables us to reduce computational complexity from n cubed to n squared. However, a major limitation of this approach is that the penalty parameter rho must remain fixed. Previous research has shown that adapting rho during optimization is crucial for stability and convergence speed in ADMM solvers. Our approach, first-order adaptive caching, solves this challenge by making rho adaptable without requiring full cache recomputation. We apply first-order Taylor expansions to update the cache variables. The 4 updates, K infinity, P infinity, C1 and C2, allow us to approximate new cache values using derivatives. Our parameter update rule is inspired by OSQP. We use the formula shown here. This balances constraint satisfaction and optimality throughout the optimization process. The update frequency is controlled by a hyperparameter tau, allowing us to balance adaptation quality with computational overhead. We evaluate our approach in 3 scenarios of increasing complexity. The hover results show dramatic reduction in ADMM iterations. Our adaptive methods, the colored lines, require significantly fewer iterations than the fixed approach, the baseline, while helping us achieve 70% performance of the full recompute. Next, we test our approach on a physical microcontroller. Our adaptive approach solves 98% of the problems in under 500 iteration limit, as compared to only 78% for the fixed approach. For our most challenging test, we evaluated performance on a figure-8 trajectory under wind. Under standard conditions without wind, our adaptive method achieves comparable tracking error while requiring 72% fewer iterations. And under wind, our method delivers 20% reduction in average tracking error and 23% reduction in maximum error compared to the fixed approach. We also deploy our approach on an actual Crazy Fly 2.1 Plus, where we subject it to wind from a fan. We see that the Crazy Fly very closely follows a figure-8 trajectory, closing the sim to real gap.